holding two magnets. You bring them close, and without touching, they snap together. Or push them the other way, and suddenly they resist, as if there's something invisible between them, saying, no, not today. Now, if you ask, why does this happen? You might expect a simple answer. The interesting part, even the greatest physicists, including Richard Feynman, would tell you that the deeper you dig, the stranger the question becomes. You see, we can describe how magnets behave with incredible precision. We can write equations, build models, even send spacecraft using these principles. But when it comes to why they work, why nature allows this invisible push and pull, we find ourselves standing at the edge of something mysterious. I think there's a neat final answer. Let's do something more interesting. Let's explore what we do understand about magnets. Along the way, discover why the question, why do magnets work, is much more fascinating than it first appears. Imagine you're folding two magnets. You bring them close, and without touching, they suddenly snap together. Turn one around, and instead of attraction, you feel a strange resistance, like an invisible cushion pushing them apart. There's no string, no glue, nothing you can see connecting them, and yet something very real is happening between those two small objects in your hands. Now, naturally, the first question that comes to mind is simple. Why? Why do they attract? Why do they repel? What is actually going on in that empty space between them? First, it seems like this should have a straightforward answer. After all, we live in a world where science explains things. Yeah, we know why the sky is blue, why electricity flows. So you might expect that magnets would come with a clear, satisfying explanation too. This is where things begin to get interesting. Because if you ask a physicist, especially someone like Richard Feynman, you won't get a simple, everyday answer. Instead, you'll be told something a bit unusual. We can describe magnets extremely well, but explaining time why they work is not so simple. In physics, there's an important difference between describing how something behaves and explaining why it behaves that way. With magnets, we are incredibly good at the how. Then, we know that magnets produce a magnetic field, an invisible region around them where forces act. We know that opposite poles attract and like poles repel. Measure these forces, calculate them, and use them to build powerful technologies, electric motors, generators, even the devices in your pockets. But when we try to go deeper and ask, what is a magnetic field really? Or why does nature allow this force to exist at all? We start running into limits. One way to think about it is this. Magnets are not just objects. They are part of a deeper structure of nature. Every magnet, there are tiny particles, electrons, each behaving like a miniature magnet themselves. They have a property called spin, and when many of them align in the same direction, their effects add up, creating the magnet you can hold in your hand.
But even this doesn't fully answer the question.
And you can ask, why do electrons have this property? And the answer leads you further into the strange and fascinating world of quantum physics. Particles don't behave like tiny billiard balls, but more like patterns of probability and energy. At that level, the idea of why becomes harder to pin down. The universe, it seems, follows certain rules. Rules we can observe, measure, and describe with mathematical precision. Magnetism is one of those rules. It's part of the fundamental behavior of matter and energy. And two magnets push or pull each other. What you're really seeing is a visible effect of something deeply built into the fabric of reality. The iron reactor that doesn't require contact, doesn't need a visible connection, and yet is as real as anything you can touch. And the more you think about it, the more surprising it becomes that something as ordinary as a magnet on your fridge is actually a window into some of the deepest ideas in physics, ideas that scientists are still exploring, questioning. But they are more completely now. Let's take the question a little further. Instead of asking what magnets do, let's look more closely at what's happening inside them. Because the real story of magnetism doesn't begin with a magnet you can see. It begins with things so small that you can't see them at all. Every piece of matter around you is made of atoms, and inside those atoms are even smaller particles, including electrons. Threads are not just tiny bits of charge moving around. They have a very special property called spin. Now, spin doesn't mean they're literally spinning like a ball, but it behaves in a way that gives each electron its own tiny magnetic effect, almost like a miniature bar magnet. In most materials, these tiny magnetic effects are all pointing in different directions. They cancel each other out, so you don't notice anything unusual in materials. Large groups of electrons begin to line up in the same direction, canceling each other. Their magnetic effects combine, reinforcing one another. When enough of these electrons align, they create what we call a magnetic domain. The domain has a small region inside the material where all the tiny magnets are pointing the same way. And when many of these domains themselves line up, the entire object becomes a magnet. So now, when you hold a magnet in your hand, what you're really holding is a huge number of tiny coordinated magnetic effects, all working together in the same direction. Of course, it's the collective behavior of countless particles acting in unison. But this raises another question. Why do these electrons line up in the first place? But why don't they just remain random like they do in most other materials? But we have to step into the strange world of quantum physics, where the rules are very different from what we experience in everyday life. At this level, particles interact through forces and principles that don't always have simple visual explanation. So one of these principles encourages certain electrons to align their spins under the right conditions, lowering the energy of the system and making that arrangement more stable. This means that magnetism is not something added onto matter. It's something that emerges naturally from the way particles behave at a fundamental level. It's built into the structure of atoms themselves. And yet, even with this understanding, we're still not at the final answer, because every explanation leads to another why. Why do electrons have spin? Why do laws of quantum physics favor this kind of alignment? Why does the universe allow forces to act across empty space at all? At some point, physics stops giving deeper reasons and starts giving descriptions of patterns that are incredibly consistent and reliable, but still, in a sense, mysterious. We can predict exactly how a magnet will behave in almost any situation, but the underlying reason those rules exist remains one of the great questions. When you see two magnets attract or repel, you're not just seeing a simple force. You're seeing the result of countless tiny interactions by rules that reach all the way down to the foundations of reality itself, where matter, energy, and the laws of nature come together in ways that are precise, powerful, and still not fully understood. Now let's step back again and look at magnetism from a slightly different angle, not just from what's happening inside a magnet, but from what's happening in the space around it. But one of the strangest parts of magnetism is that the force doesn't seem to need contact. It reaches out through empty space and affects other objects at a distance. Take a small piece of iron near a magnet. It begins to move before it even touches it. That alone should feel a bit unusual. In life, we're used to forces that require contact, pushing, pulling, hitting. But here, there's something acting where at first glance, there appears to be nothing. To make sense of this, physicists use the idea of a field. A magnetic field is a way of describing how a magnet influences the space around it. Instead of thinking of the force as jumping directly from one object to another, we imagine that the magnet creates a condition in the space nearby. And when another magnetic object enters that space, it responds to that condition. Like temperature. If you walk into a warm room, You don't ask how the heater is directly touching you. But the warmth is simply present in the space, and your body reacts to it. In a similar way, a magnetic field is there, filling the space around the magnet, even though you can't see it. Now, this idea of a field might sound abstract, but it turns out to be one of the most powerful concepts in all of physics. It doesn't just apply to magnets, it also applies to electric forces, gravity, and even more fundamental interactions. Much of modern physics is built on the idea that fields are just as real as objects. Scientists can map these magnetic fields using iron filings, which arrange themselves along invisible lines, revealing patterns that show how the force is distributed. Curve from one pole of the magnet to the other, forming shapes that help us visualize something we otherwise couldn't see. But even here, the deeper question remains, really? Is it something physical, like a substance? Or is it just a mathematical tool we use to describe how forces behave? If you ask someone like Richard Feynman, the answer might be surprising. That the field is as real as anything else in physics, not because we can touch it, but because it consistently describes what happens in experiments out of the language nature uses, even if it doesn't fit neatly into our everyday intuition. And the more you think about it, the more this idea challenges the way we normally understand the world. We tend to think of empty space as truly empty, as nothing at all. But magnetism suggests that space itself can have properties, can carry effects, can influence what happens within it. Yes, imagining magnets sending out invisible signals or forces in a direct line, it's more accurate to think of them as shaping the space around them. And other objects respond to that shape, almost as if they are following the contours of an unseen landscape. This way of thinking shifts the question once again. Asking how magnets reach across space, we begin to ask what space itself is capable of doing. And that leads us deeper into the foundations of physics, which are objects standing between objects, and the space they occupy becomes less clear, and where even something as simple as a magnet reveals layers of complexity that are still being explored. Now, looking at what's happening inside magnets and around them, we can return to the original question with a slightly different perspective about magnets, or how do they behave. But once again, why do they work at all? And this is where things become even more subtle. Especially in physics, the word why can be a tricky one. When we ask why, we often expect a reason that feels familiar, something connected to everyday experience. But nature doesn't always organize itself according to what feels intuitive to us. If you were to ask a deeper and deeper chain of why questions, you might notice something interesting happening. You get explanations that feel satisfying. Magnets work because of magnetic fields. Magnetic fields exist because of moving charges and the properties of electrons. Electrons behave the way they do because of the laws of quantum physics. Then you reach a point where the answers stop becoming explanations in the usual sense and start becoming statements of how the universe is structured. That way, at that level, physics doesn't always tell you why the laws are what they are. It tells you what the laws are and how they work. It gives you patterns, relationships, and equations that describe reality with incredible accuracy. And magnetism is one of those patterns. Magnetism is closely tied to electricity. The two are not separate phenomena, but different aspects of a single unified interaction known as electromagnetism. The idea was brought together in the 19th century by scientists like James Clerk Maxwell, who showed that electric and magnetic fields are interconnected and that changing one can create the other. This means that when you observe a magnet, you're not just seeing an isolated effect, you're witnessing part of a much larger framework that governs how charged particles interact. Advance that cause a magnet to attract iron are also responsible for light, radio waves, and much of the technology we rely on every day. But even knowing this, the question of why it just moves deeper. It just moves deeper. Why does electromagnetism exist? According to Maxwell's equations, why do particles have charge or spin or any of the properties that give rise to magnetism? And here, physics reaches a kind of boundary, not a failure, but a limit of the kind of answers it can provide. It can build models, test them, refine them, and use them to make predictions with astonishing precision. Attica don't always step outside the system and explain why the system itself exists in the way that it does. That Richard Feynman often emphasized that the goal of physics is not necessarily to satisfy our sense of curiosity with simple reasons, but to uncover the rules by which nature operates, even if those rules feel unfamiliar or even strange. So when you hold the magnet and feel that invisible push or pull, you're encountering one of those fundamental rules. A trick, not an illusion, but a direct expression of how the universe behaves at its most basic level. And perhaps the most fascinating part is not just that magnets work, but that we are able to understand them at all, to describe their behavior, to use them in technology, and to keep asking questions about them, even when those questions lead us to the very edge of what we can explain.